Prior to this lesson, we have been working with radical expressions, and we've worked with multiplying and we've worked with adding and subtracting. So today what we're going to be focusing on is division, and also how to make sure that we don't have rationalizing denominator, which means not having the radical expression in the denominator. So looking at the first part that we're going to be looking at is if we are dividing two radical expressions, okay, you can actually, there's a property that allows you to say, well, as long as the roots are the same, so notice how my indexes are the same. If the indexes are the same, I can then rewrite the whole expression underneath it. And in doing so, it will allow me to actually reduce my fraction. And then I can look at my index and simplify from there. So let's look at the example here. Here I have the cube root of 32, and I'm dividing by the cube root of -4. They both have the same index, so I'm able to rewrite them by saying the cube root of 32 divided by -4. Well, we can look at then this fraction and actually reduce it. So I can say 32 divided by -4. I know what that is. That's actually -8. So I can then rewrite this expression as the cube root of -8, because 32 divided by -4 is -8. In looking at them, I can say, okay, well, what might be a simplification? Is there a cube root of -8? Well, 8 can be broken down to 4, 2, and 2. Or 4 and 2, and then 4 can be broken down to 2 and 2. I'm looking for a cube root of 8, so it means 3 of a kind. I have 3 2's there, which means I can pull a 2 out. So I could say it's 2. However, because the number is negative, I know that I need to have to be a negative number. So -2 times itself 3 times would give me -8. Another thing I could have done is I could have looked at my chart that I have, and I could have gone to the cube root column and looked for 8 and see if there's a cube root, and there is, and it's 2. Because 8 is negative then, and it's an odd index, I know that 2 would need to be negative as well. Okay? Alright, let's look at another example. So here I have the cube root of a value divided by the cube root of another value. So I know that then I can do the property. The property allows me then to rewrite this all underneath one radical. So I can do the cube root of 162 x to the 5th, all divided by 3x squared. By writing it this way, it allows me to look at the fraction inside, and I can now reduce it. So if I reduce 162 divided by 3, I can look at the cube root, 162 divided by 3, and that equals 54. Then I can do my x to the 5th divided by x squared. Again, the properties for exponents when you are dividing and subtracting. So 5 minus 2 is 3, so I have x cubed. At this point, I would then look to see if I can take the cube root of anything. If I look on my sheet here, I do not see that the cube root is a perfect cubed, so I'm going to go to the simplification. So I would then say 54 can be broken down into 27 and 2. 27 is 9 and 3, and that is 3 and 3. So I'm taking the cube root, so it means I need 3 of a kind. So I'd look to see if I need 3 of a kind. I do. I have 3 3's. So I can pull a 3 out. So I pull that 3 out. I'm left with a cube root of 2 underneath the radical sign. Then I look to my x cubed. Well, x cubed, I need 3 of a kind to pull it out. So 3 divided by 3 is 1. So I can pull out 1x. So therefore, this simplifies to 3x cube root of 2. So that would be your final answer. Okay. Alright, let's look at this next example. So I have the 4th root of an expression over the 4th root, so I can rewrite this as the 4th root. And I would do the 1024 x to the 15th all over 4x. So then I can look at each value, and I can each fraction here, and I can reduce it. So 1024 divided by 4, reducing this, becomes the 4th root of 256. And then I have x to the 15th and x, so again the properties, this is subtract, so I have 15 minus 1, so that's 14, so it's x to the 14th. So I look to the fourth root and I see, is there anything I can do to get rid of, is 256 a fourth root? So I look on my sheet and it is, the fourth root is 4, so I could just write 4, and that's going to be the fourth root. And then I look to x, so I could, if I take 14, I need 4 of a kind, 14 divided by 4, it's going to be 3, I'm left with 2. So I could pull 3 out, and I'm left with 2 underneath. So I have x cubed, I pull out, and I have x squared that I'm left inside. So this becomes my final answer. Okay? So again, once you have, if you have two radical expressions being divided and they're the same index, you can rewrite them as one expression and then reduce inside and then simplify. Okay? Well, now we have this term called rationalizing the denominator, and what that is you do not want to have a radical in the denominator. You do not. So notice here I have a radical expression. Now, if I would rewrite this as what we just did, this would be the square root of 2 over 3. I can't reduce it any further than this. So at this point I actually have a radical expression in the denominator, and I don't want that. So to get rid of a radical expression in the denominator, you need to multiply it by a value that makes it a perfect root, meaning I have the square root of 2 over the square root of 3. I'm looking for a root of 2 or an index of 2, so I need to find something that would allow me to get rid of this radical expression. So if I would multiply this by the perfect square, since I'm looking at square roots, or make this a perfect square, multiply something that makes it a perfect square, then the square roots are going to cancel each other out. And I can say that if you just think about the following. If I have the square root of 5, and I multiply it by the square root of 5, what does that equal? Well, it equals 5 times 5 underneath the square root, which equals the square root of 25. Well, what's the square root of 25? It's just 5. The answer is 5. The radical sign goes away. Okay, so remember how 5 squared is 25, and we take the square root of 25, it is 5. So 5 is the answer. So the square root of 25 becomes 5. The radical sign goes away. So what I'm trying to find is a value that I can multiply the square root of 3 by to make the radical sign go away. Well, if I'm talking about a square root, I could just multiply it by itself, and then it should go away. Well, what we want to be focusing on is a thing called the magic 1. Okay? And you want to multiply the denominator by that value. You're going to multiply both the denominator and the numerator because it's a 1. And you want to find what the magic 1 is. So basically, anything over itself is 1, right? So 2 over 2 is 1. Okay? The square root of 3 over the square root of 3 is 1, right? So this is what I mean by the magic 1, where you're going to be multiplying by a fraction that is really 1, but it's a magic number because it will get rid of the radical sign. So let's look at this. If I have the square root of 2 divided by the square root of 3, if I multiply both numerator and denominator by the square root of 3, I'm really multiplying it by 1. That's the magic 1. In doing so, look what happens. I'm going to get the square root of 2 times 3 on top, and on the bottom I'm going to get the square root of 3 times 3. Okay? Well, square root of 2 times 3 just becomes the square root of 6, but the bottom becomes the square root of 9. Well, what's the square root of 9? It's really 3. So this becomes the square root of 6 over 3. Okay? So in multiplying this fraction by the magic 1 with a value that allows me to make it a perfect square, I can get rid of that radical expression. Okay? So when I have a square root, the square root of 3, to get rid of it I need to multiply it by itself. So I'm trying to look to find a way to make it a perfect square. So let's look at another example. So I have the square root of x cubed over 5x to the y. Okay? Well, what I want to do first probably is to rewrite this as x cubed all over 5x to the y. This allows me to reduce as best I possibly can before I need to move forward, because maybe I can get rid of the denominator for all I know. Okay, I can't get rid of the values of the numbers, but I could reduce my x's. So I have 3 on top and 1 on the bottom, which means I just end up having the bottom one cancels and the 3 becomes a squared. So this becomes the square root of x squared on top. And this is 5. The x went away and it's y. Okay, so that reduced to this. At this point, I would then see how I cannot reduce any farther. I have a denominator, so I need to get rid of this denominator. So that's like rewriting it as the square root of x squared all over the square root of 5y. Okay? So what would I need to multiply? What would my magic 1 need to be so that this radical sign cancels out? Well, I kind of want to multiply by itself, wouldn't I? Because I'm looking for a square root. I'm looking for something. Remember, the square root is something times itself. Okay? So, in doing that, I'll multiply by the square root of 5y over the square root of 5y. When I do that, my top becomes the square root of 5x squared y. I'm just rearranging the top, so it's like x squared times 5y. My bottom then becomes the square root of 5 times 5, which is 25, and y times y, which is y squared. I can then reduce my bottom because the square root of 25 is 5, and the square root of y squared is just y. So this then becomes simplified as the top stays the same, but then the bottom can be written as 5y. Because the whole point is to create a perfect root here, a perfect square here, that allows me to then take the square root of it. So the square root of 25 is 5, and the square root of y squared is y. So now I can reduce it, and that would be my final answer. Okay? Alright, let's look at the next example. So this one's a little bit different in the fact that it's a cube root. So when it's a cube root, alright, I can't reduce the inside fraction at all anymore, so I'm going to rewrite this as the cube root of 2 over the cubed root of 3x. Okay, so I need to make it a perfect cubed. So I need to be able to take the value out, so 3 of a kind, to be able to pull it out. So I currently have 3x. So what would I need to multiply 3x by to make it a perfect cube? Well, 3, a perfect cube is 27, okay? And x, a perfect cube, is x cubed. So how can I make 3 the value of 27? What should I need to multiply it by? Well, I need to multiply it by 9. X, what would I need to multiply it by to make it x cubed? Well, I need to multiply by x squared. If you notice, 9x squared is really 3x twice. So 3x times 3x equals 9x squared. Okay? Well, if I multiply 9x squared by 3x, I'm going to get 27x cubed. That is a perfect cube that would allow me to then remove it out of the radical sign. Well, if I multiply the denominator by 9x squared, I have to multiply the numerator by 9x squared. Okay? And in doing so, then, again, this is underneath the radical, the cube root. And in doing so, then, I can then merge the two together. So I'm going to do the cube root of 2 times the cube root of 9x squared, and that becomes the cube root of 2 times 9x squared on top. And then the bottom is going to be the cube root of 3x times 9x squared. In doing that, then the top becomes the cube root of 18x squared, and the bottom becomes the cube root of 27x cubed. Well, 27x cubed really is, the cube root of 27 is 3, and the cube root of x cubed is x. So therefore, I can finally rewrite this as 3, the cube root of 18x squared. There's nothing I can reduce on that, and then it becomes 3x on the bottom. So you're trying to find a value that you can multiply by, that then when I multiply them I get a perfect cube. Worst case scenario, if it's a cube root, take what's inside of your radical sign and multiply it twice for what your magic 1 will be. Okay, so notice how 3x times 3x becomes 9x squared. So I'm taking twice the value and then multiplying with that, and it becomes the cube root. Because remember, a cube root is anything times itself 3 times. On the squared, it'd be anything times itself once or twice. So that's why I did it again. Here, after reducing it, then I did 5y times 5y because it was a squared. So worst case scenario, you could just multiply it by itself as many times as the index is. Okay, and that way you would know. Okay, so if I look at the square root of 7 fifths, okay, so it's like the square root of 7 over the square root of 5. Well, what do I need to multiply the denominator by to make it go away? Well, I need it to be a perfect square. So I want to multiply by square root of 5. And then be square root of 5. In doing that, on the top I get the square root of 35, and the bottom I get 5. Because square root of 5 times square root of 5 is the square root of 25, and that becomes 5. So that is my final answer on that one. Okay? Alright, so now you have 3 examples here on the bottom I'd like you to try on your own. And then once you've tried them, go ahead and pause this, go ahead and try it, and when you come back you can check your answers. Okay, so looking at this example here, I want to find a perfect square to get rid of this radical sign. So to make the shortest, I could just take the 4x to the 8th, the square root of 5y to the 9th, and I could just multiply by the magic 1 of the square root of 5y to the 9. Okay, because I know anything times itself is going to give me the square root. I'll get a perfect square. In doing that, the top becomes 5 times 4 is 20. And then I'm going to have x to the 8th over y to the 9th, and that's the square root. On the bottom, okay, I'll get the square root of 25, y to the 18th. Because the rule of exponents is you add them when multiplying. So then I want to simplify as best I can. So, in looking at the bottom, I'm going to have 5 y to the 9th. Okay? Square root of 25 is 5. Square root of y to the 18th is going to be y to the 9th. I need a pair to pull them out. I have 9 pairs. Now look at the top. Now the top, the 20, the square root of 20, so 20 can be broken down into, so if I do the square root of 20, it can be 5 and 4, and it can be 2 and 2. So I can pull a pair of 2's out, so I'll have 2, okay, and then I have the square root of 5 underneath it. Then I look for my x to the 8th. The square root of x to the 8th is going to be 4. I can pull out 4 to the x to the 4th. And I have y to the 9th. I can pull out 4 y's. I can pull out 4 y's. Oops. Sorry about that. I can pull out 4 y's, and then I'm left with 1 y underneath. Okay? So at this point then, my answer becomes, let me erase this so we can see it, becomes 2x to the 4th, y to the 4th, square root of 5y, all over y, 5y to the 9th. But notice how now I have the y's pulled out, I actually can reduce these a little bit, can't I? I can take this 4y, if you have y's being divided, you subtract them. So I can take 4 minus 9, so I have the 4 that cancel here, and I have 5 on the bottom here. So then the actual final answer becomes 2x to the 4th, the square root of 5y on top, and on the bottom becomes 5y to the 5th. Okay? So again, you multiply by the magic 1. When you take the square root of everything, it cancels out the radical sign, and then you can simplify and then reduce. Alright, let's look at the next one. So this is going to be the cube root of 4 all over the cube root of 5x squared. Okay, so I'm looking for a cube root. I need a number to make it a perfect cube. Well, 5 is a perfect cube of 125. So I need to multiply 5 by 25. Okay, and then I need to multiply x squared. Well, to make x squared a perfect cube, I just need to multiply it by x. Okay, so there's the cube root of 25x. So if I multiply the bottom, I gotta do the top part by it. Cube root of 25x. So when multiplying across, I'm going to have 25 times 4, which is going to be 100x, the cube root of it. And then on the bottom, I'm going to have the cube root of 125 x cubed. Okay, so the top part becomes the cube root of 100x, and the bottom then, the cube root of 125 is 5, and the cube root of x cubed is x. Now I just have to simplify this. So the cube root of 100, if I take 100, it'd be 10 and 10, and then it's 5 and 2, and 5 and 2. And I don't think I can actually reduce it any more than that, can I? So at that point, I just leave it as is. So once you know you can't reduce it, then that just becomes your final answer. And one thing I just want to make sure I'm showing, and I'm not probably doing a very good job of it, is this is the cube root, so it's up above here. It's not 3 times that value. Okay, so just to make sure that you realize that. Okay? Alright, so let's look at the next one. So you had the cube root of 7 all over the cube root of 2xy squared. Okay, I can't reduce anything in the inside, so now I resort to that. So now I need to multiply the denominator by something that makes it a perfect cube. Well, 2 to become a perfect cube would be 8, so I'd want to multiply it by 4. Okay. And then x, to make it a perfect cube, I need to multiply by 2 more x's. And then y squared to be a perfect cube, I need to multiply by 1y. Okay? So if I take this and I multiply it, I'd have 8x cubed y cubed, and that would be a perfect cubed. So I need to multiply the top by it. Okay? At this point then, let's multiply the top. So 7 times 4 becomes the cube root of 28 x squared y. Okay, multiplying those together. On the bottom, it's going to be the cube root of 8 x cubed y cubed. Okay, that is a perfect cube now, so I can take the cube root of each one of those. So then the bottom becomes the cube root of 8 is 2, the cube root of x cubed is x, and the cube root of y is y. And then I want to see if I can simplify this anymore. So 28 is going to be 7 and 4, and that's 2 and 2, so I really can't reduce anymore. So this just becomes the cube root of 28 x squared y. And then that would be your final answer. Okay? Okay, in turning the paper over, the next thing that we're going to be looking at is multiplying what's called conjugates. And conjugate is a word that refers to kind of like the opposite. A conjugate with a binomial is going to be the first term and the second term the same, but what the difference is the middle term is different. So if I have, let's say, the square root of 3 plus the square root of 2, its conjugate is going to be the exact same thing, so the square root of 3 and the square root of 2, but the sign in the middle will be opposite. Okay? So this second value is the conjugate of this first value. And the reason why conjugates are important is because it actually allows us to get rid of radical expressions. So watch what happens when I have the conjugate of each other and I do the distributive property. So I take the square root of 5 times the square root of 5, I'm going to get the square root of 25. I take the square root of 5 and I multiply by the negative square root of 6, I get minus square root of 30. I take a square root of 6 and multiply it by the square root of 5, and I get a positive square root of 30. And take the square root of 6 and multiply by negative square root of 6, I get negative square root of 36. Okay? At this point, I can simplify. What's the square root of 25? That is 5. I can combine these two, a negative square root of 30 and a positive square root of 30, they actually cancel out. And then I have a negative square root of 36, or minus a square root of 36. Well, what's the square root of 36? It is 6. So it's going to be 5 minus 6. Okay? So what is 5 minus 6? It's negative 1. So notice how I have an actual whole number answer. I have a value. I don't have a radical. The conjugates allow you to do that. And the reason that is because the middle terms cancel themselves out, because you have a positive of it and you have a negative of it, because they're exactly the same, right? So the conjugates are useful in the fact that it will get rid of the radical expressions. Your first and your last term will always be a number because they're being multiplied by itself, and anything multiplied by itself is itself. The square root of it is itself. So why is this important? Well, if you notice in the examples down here, we have fractions, but they're not just radical expressions. They actually have other numbers with them. They're binomials. So how would I get rid of a radical within this? So my magic 1 at this point, so my magic 1 value that I'm going to use is going to equal my conjugate. Okay? So whatever I have in the denominator, I'm going to multiply by its conjugate, and that will get rid of any radical expression. So my conjugate of 1 minus the square root of 5 is 1 plus the square root of 5. And whatever I do to the bottom, I have to do to the top. Okay? So then, they're being multiplied, because that's what we're doing, so I can do the distributive property. Well, if I look at the bottom, 1 times 1 is going to be 1. I have a negative square root of 5 times 1, and I have a positive square root of 5 times 1, so those actually cancel each other out. If you don't see that, I'll just go ahead and do it so you see it. So a positive square root of 5. I have a negative square root of 5 times 1, which is a negative square root of 5. And then a negative square root of 5 times a positive square root of 5 is going to be a negative square root of 25. So these are going to cancel. I have 1 minus the square root of 25, which is 1 minus 5. So that equals negative 4. So my bottom equals negative 4. Okay, so that equals negative 4 from there. My top here is going to be 3 times 1, which would be 3. 3 times the square root of 5, which is plus 3 square roots of 5. I have a square root of 5 times 1, which is plus the square root of 5. And the square root of 5 times the square root of 5, which is plus the square root of 25. Okay? Well, the square root of 25 is actually 5, right? So this can just be 5. So if I combine my like terms, I can take my constants, which is 3 plus 5, and I'm going to get 8. And then I take my radical expressions, which is 3 square roots of 5 and a square root of 5, so it's 3 plus 1, and you have plus 4 square roots of 5. Okay? At this part, I'd like to say, yes, that is my final answer, but you want to make sure that you can't reduce it any farther. Okay? So what I would do is I would take this and write it over. I'd do 8 over negative 4, because remember the denominator is over each expression. And I have plus, and then I have 4 square roots of 5 over negative 4. So I've just taken that negative 4 and I've kind of put it over each one. I can reduce this with 8 divided by negative 4, that's negative 2. And then what's 4 divided by negative 4? That's a minus 1 square roots of 5. So then really it's negative 2 minus square roots of 5 in your final form. Okay, so you can go down to each one of these. It's kind of like a reduction. Alright, go ahead and try this next problem here. And then when you are done, go ahead and pause it, try it, and then when you're done, come back and compare your answer. Okay, in looking at this problem, you do have a binomial in the bottom, and you want to get rid of the radical sign, so you want to multiply by its conjugate. So my conjugate is going to become 4 minus square root of 7, and that's going to be over 4 minus square root of 7. That's my magic 1. That's a 1, right? So now I'm going to do the distributive property. So if I do the top, it will be 5 times 4. That's going to be 20. I have 5 times the square root of negative 7, or negative square root of 7. That's going to be minus 5 square root of 7. I have a 4 times the square root of 7, so that's plus 4 square root of 7. And then I have a square root of 7 times the negative square root of 7, and that is going to be minus square root of 49. That's the top. On the bottom, I'll have the 4 times 4, which is 16. My middle terms, my 4 times the negative square root of 7 and my 4 times the square root of 7, will cancel each other out, so I don't have it to do with that. And I just have the square root of 7 times negative square root of 7, that's minus square root of 49. So now I can kind of simplify and reduce. So I have 20 here. I can combine my square root of 7, so that's a negative 5 plus a 4, that's minus square root of 7. And then I have a negative square root of 49, which is just minus 7. My bottom then becomes 16. I have minus square root of 49, that's minus 7. So now I can combine my constants up top, and that's going to equal 13 minus square root of 7, and that's all over 9. I can't reduce any farther. I could rewrite it this way if I wanted to, 13 over 9 minus square root of 7 over 9, where I take the denominator and split it between both. And that then would be my final answer. So today what we've looked at is we've looked at dividing radical expressions, in which then if they have the same index, you can then write them all underneath 1 and then reduce as best you can. And then once you get that reduced, you can apply the index and see what your answer is. Same thing with exponents. You're following the variables, you're following the rules of exponents of subtracting when you're dividing. Then we looked at how to get rid of radicals underneath the denominator by multiplying by its perfect square or cubed or whatever it needs, whatever the index is. You want it to be a perfect root. So I have a square, I want it to be a perfect square. Here I have a cubed, so therefore I want it to be a perfect cubed. What do I need to multiply the top and the bottom by, so my bottom is a perfect cubed or a perfect square, whatever your perfect root is? What do I multiply the bottom by? I have to multiply the top. The bottom then will cancel out, where it becomes an actual non-radical expression. Okay, so it'll become non-radical. The top then gets multiplied and simplified if needed. Then we talked about conjugates. And conjugates are where you multiply by the same expression, but the sign in the middle is changed. And that allows the middle terms to cancel. And then the two end terms then are perfect squares and then become numbers. So your number then is a rational number. That's important when we're dealing with binomials being divided. So when we have the fractions, you want to multiply the magic 1 would be its conjugate. And that means that the bottom then gets rationalized out and is not a square root, or does not have a radical in it. And then you multiply the top as well, and then you simplify as best you can. So it's kind of what we did today. So your homework then is going to be page 254, numbers 25 through 30, 39, 41, 43, 45.